We are wrapping up with several threads today. We are finishing up with alternative energy. And I just wanted to say that with regards to alternative energy and really all of the things we talk about in this class, it's quite frustrating as an educator to have to really just give you the bare minimum of things. And there's so much more you could say about the tremendously exciting field of alternative energy. I just gave a 3-hour short course yesterday morning at the Harvard Law School on alternative energy technologies, and I was able to go into much more detail than we have time to get into. I say this because the slides that I use for a short course of this nature are much more text heavy because they're intended also to be a resource for people who take the course and then want to read it later rather than a visual aid for students who are going to be responsible for the material. So I will put that on Canvas under files for those of you who have an interest in alternative energy and want to take it into a little more detail. These are the things, the technologies that I think are a good place to start. If you look through those, if you see them, and they are of interest to you, certainly there would be a place for you to put those on the next quiz if you wanted to look at them. And again, it's a lot more text than it is pictures, but it goes into 7 different innovative new types of solar. So including things like solar roadways, including these flexible fiber optic cables, essentially, that are thinner than a human hair and can be woven into fabrics, all sorts of really neat things, including an economic discussion of the fact that of the 3 traditional solar photovoltaics that we use, there's monocrystalline, there's polycrystalline, there's amorphous, and it's an interesting economic situation where monocrystalline are the most expensive to make, but they are the most efficient. On the other end, you have amorphous, which is the least expensive to make, essentially slosh some silica, molten silica, into a pan and let it dry. Those are the least expensive to make, but they're the least efficient, approaching something like 4%. And so you have to make these economic decisions because, you know, how long are you going to have those panels out? I told you about in the upper level class, we go to the roof of a building and look at these panels. The manufacturer guaranteed them for 20 years, but they were installed in 1981 and they've not had any significant decline. So a lot of the alternative energy technologies that we're talking about rest in the notion of economics. How do you make a good, sound financial decision about what technologies in which to invest? And then last night I made mention of, I think 1 or 2 of you came, of a field trip that I took to the Weston Observatory last night with the natural disasters class, talking about Fukushima, talking about, well, this is sort of a segue into these slides, talking about how does the engineered environment, right, with Fukushima, we're not talking about the natural disasters in this class, but there was a, you know, very, very high seawall, and the people had such what is this word? I'm sorry, I've been up all night. Coffee is not doing it this morning. Confidence in the engineered structures that they were actually standing on the seawall watching the waves come in. And when the waves were larger than what policy and scientists decided could be the largest possible earthquake ever in the area of Tokyo, which is an 8, when we had a 9.2 and it generated 100-foot tall tsunami waves, those people were toast, as was the nuclear reactor. So I'll put in, or I have in the slides that I'll put up as sort of supplementary reading, a lot of information about the disaster, such as 3 Mile Island, which is almost a disaster, but it was close to here, about Chernobyl, which was a really badly designed, badly run plant, and then Fukushima, which was a state-of-the-art plant. They had already had a couple of the reactors shut down for scheduled maintenance, and I don't think this has enough juice, and shut down a couple more, but still there was a disaster that is ongoing. It's still going on in Japan, and you might say, okay, I don't live in Japan, who cares? We have now irradiated shellfish on the west coast of the United States because that disaster spread this nuclear radiation across the largest ocean basin in the world. And now, you know, if I were telling people about what to eat, which I do in other classes, I would say don't eat shellfish from the West Coast, especially those where you eat the whole body. clams. If you eat just the adductor muscle, so scallops, they cut a muscle off and you eat that. Clams, anything you eat the whole body, shrimp, nope, no more out there. So this impacts our food system, this impacts economics, and this impacts the future of what sorts of technology we use. So anyway, nuclear energy, we looked at that slide with the controlled, go back up to it for 1 minute. Controlled fission of uranium, which is naturally occurring. So when we're thinking about these energy technologies, recall this is an alternative energy technology in that it's an alternative to fossil fuels. However, it is not a renewable energy technology. We mine uranium. And so the mining impacts are actually on par with things like coal, because uranium exists in very, very small concentrations naturally occurring in rocks. And so we have to bust up and separate out huge amounts of rock to get that uranium. And then plutonium is not naturally occurring, so we actually do things that are beyond the scope of this class to get the plutonium. But a nuclear reactor, and I'll show you a picture in the next two slides forward, works in theory in a very simple way. So I'll show it to you, but let me describe it to you first. And these are, these are traditional reactors that are in place now. I've invited you all to the nuclear power plant that we're going up to next week with my alternative energy class. This is the kind of stuff that's operating now. In the slides that I'll provide for you, there are lots and lots of smaller, scalable, less waste, molten metal breeder reactors, all sorts of neat, innovative things. However, I'm not teaching you guys about them because they're not in operation right now. They're just sort of things that we can do in the future. So there is a future technology, but the one that's in place is quite simple and somewhat dated. We take the heat that is obtained from the splitting of the uranium molecules, and we boil water. That's it. Because when you boil water, you turn it into steam. Vapor can influence pressure, right? So vapor is now pressurized. It gets forced through a turbine, just like all these other technologies we talked about. The turbine is creating a rotational field. When you put that in the presence of a copper coil, you create an electromagnetic field and you harvest the electrons. And electrons are the energy. So then what you have to do is you have this steam. You can't just leave it steam. So you have to cool down the steam. And the way you do that is by those big cooling towers maybe you associate with power plants. When we go to Pilgrim, they don't have a cooling tower because they have the ocean right there. So really a cooling tower is if you need to cool down the water a little bit, the steam a little bit before you discharge it into a surface water body, so a river or estuary. But we have cold, deep water down in Pilgrim, so they don't even need that. So you cool down that water, and then you recirculate it back through the heat of this reaction, turbine, generator. It just keeps going on in these 3 loops. I'm going to skip this next slide because that is, every time I skip a slide, it makes me reorient this. So this is a picture. This is in your book. The picture comes up, yeah. This is in your book of a nuclear power plant. And the book has a good description. Sorry, every time I do this. To do it again? Yeah, okay. The book has a good description of this. So here we are in the main phase of the power plant. You're looking down on it, essentially. You have the reaction going on. Reaction going on in this main part, the orange part here. The atoms of uranium are being split by neutrons. Neutrons are released, and you have a chain reaction of more and more and more uranium atoms being split. Every time you split, you generate heat. You can also do this with plutonium. What happens then is you have to have a moderator and control rods. You see the moderator of those cement walls, and then control rods. Both of them moderate or temper the amount of metals that have been split, the uranium metals that have been split, by absorbing neutrons. So you suck neutrons away, you don't have an uncontrolled reaction where you're splitting too many. That is a meltdown. When your moderator is faulty, when your control rods are not coming in and out at the right rate, then you make too many neutrons, you split too many uranium atoms, and you end up with meltdown. The heat can no longer be contained despite numerous fail-safes in the equipment, and you end up with explosions, burning, very, very high temperatures, and a lot of radiation released. I don't have this in the presentation, but in your book, there's a rather troubling slide dealing again with economics and with policy that shows the Chernobyl meltdown and the fallout that was emanating from that covered Europe and is especially high in the United Kingdom. And this was the Soviet Union when this went on. And so that government is now dissolved, and so there's no one to assign blame, no entity to whom to assign blame and to get compensation for the many, many deaths, again, beyond the scope of this class. But anyway, that melts down, you're in trouble. That melted down in Chernobyl, that almost melted down in 3 Mile Island, and that melted down and is still in a state of unrest in Fukushima after the Tohoku earthquake. So there's the heat. The heat is in this self-contained chamber, the coolant. It's a coolant, it's an organic liquid that has a high capacity to hold heat. So it's just going around in here. The pump is pumping this through into the heat exchanger. The heat exchanger now has water that is just what I said, turns into steam, turns a turbine, powers a generator, generates electricity. You see the useful energy is only 30%. You have to then subtract from that the energy you used in mining. And so the energy efficiency of these is quite low. So then you have the steam turning a turbine, powering a generator. You have to cool down that steam. So you have water source, and this is where the cooling tower comes in. The cooling tower takes water from a surface water body. You hope an ocean, because that's really large volume of usually cold water. You circulate that, again, not in contact with the steam water. That's called black water. It just goes through in a chamber, like the cooling jacket in the Miller experiment, and then it comes out and you dump it out. We'll return to this when we talk about water pollution, because these are designed well. You're not releasing any radiation into the surface water body. You have 3-step removed circulating chambers, and you're not, they're trivial amounts, but those of you who want to go on the field trip, you have to wear radiation badges, you have to get radiation checks at every point along the way. They're very, very careful about not letting any radiation get out into the public. That includes on people's bodies who have toured the plant, which they rarely allow people to do. The problem here is that you are raising the temperature of the water around the plant. So again, we'll refer to this when we talk about thermal pollution of water. In a sense, you're not changing the chemical qualities of the water directly. You're just raising the temperature. But when you raise the temperature, 2 things happen. The warmer water is, the less oxygen can be dissolved in it. So you deplete the water of oxygen, which is not good for the animal aspect of the ecosystem. The other thing you do is to increase the propensity of the water to have dissolved solutes in it. What that means is that the warmer water is, the more it dissolves things. We've already talked about water's tremendous capacity to dissolve things. You expand on that when you heat water. So there could be metals, there could be toxic things, organics, sitting harmlessly in the sediment beneath or downstream of the cooling tower, and adding heat in will mobilize them, make them biologically able to be taken up, and put them into the food chain. So though you're just warming water, it could be, have unintended chemical consequences. Funny because I brought a Harvard group last semester to Pilgrim, and some of the engineers who were touring us around were talking about how, we come here on our days off because we like to fish here. And they go to the effluent of the nuclear power plant, and it's really warm there, so there's some algae, and the fish go crazy there, so they fish there. And it's an interesting thing to know because it shows that there is thermal pollution going on, but also it shows the degree of confidence that these engineers have that they're not releasing radioactivity into the environment. So it's kind of neat it's like, you could swim in here. I was like, yeah, we kind of do too. So it's warm, you can swim, fish. And they're certain enough that they're feeding these fish to their family. So a long list of pros and cons. And again, as with fracking, this is more an emotionally charged issue than it is a true indicator of the prudence of using this in different countries as an energy strategy, stopgap or permanent energy strategy for the future. So I've already kind of talked about all these, and again, you have access to these slides, but we have vast amounts of uranium naturally occurring in rocks. It's the reason that it's not a good idea to have a basement apartment in Boston, because there's actually a lot of uranium in the rocks around here. It's releasing radon, another topic which we'll talk about later. So lots and lots of rocks have uranium in it. And so we can mine that. And without accidents, and again, not including the mining, you have a pretty low environmental impact. You do release some carbon dioxide, but it's about 30 times less as traditional power plants. So we have fairly low impact if you have a good, well-run, well-operated plant. So you have some land and water disruption, and you have the fact that these are all over the world. And they've been all over the world for quite a long time. And you can point to some places where, ooh, there was a problem. And you can point to some places that the problem was devastating. But when you compare that against a number of plants, France, for example, gets about 80% of its energy through nuclear, if memory serves. Don't quote me on that, but a huge amount. And they've never had a problem. So this is something that you have to be much more careful with than you do with, say, windmills, right? The disadvantages, there are huge subsidies. There's a huge nuclear lobbying group that wants this to be the energy of the future, so vested interest, because that's from whence comes money for them. And the environmental impacts are staggering and worldwide when there are problems. I forget what I said to you, but the Fukushima plant, yeah, I did say this, I think. Fukushima plant, finally, just a couple of months ago, the final report came out that said this was not a result of a natural disaster, despite the tsunami. Those who are operating the plant should have known better how to shut this down, should have not had to search around for the original blueprints to the plant in order to open up the containment and to fix this. So this was a situation that was deemed operator error, even though there were 100-meter tsunami waves coming in, overwhelming the plant, destroying their connection to the grid for electricity, and destroying their generators, which are their backup energy source. The other thing that we'll continue to talk about when we talk about soil and solid waste is this kind of terrible notion of where do we put this stuff? Where do we put the waste? There's lots of different types of waste. Again, I don't want to get into too much detail. There's high-level waste. There's low-level waste. There's stuff that's going to be radioactive for a short time. There's stuff that's going to be radioactive for thousands of years. We've looked into reprocessing this, so getting it more concentrated and using it over again, which would be a good thing, right? To keep kind of using as much of the usable stuff as you can. It removes stuff from the waste stream, but the fact is there's a lot of waste. And I think in this slide, if not in the ones that I'll provide for you, there's this huge battle with Yucca Mountain. Yucca Mountain has been determined by United States geologists to be the most appropriate place to store the high-level radioactive waste from nuclear power plants throughout the country. And it's a lot of, again, political wrangling. There's a lot of not in my backyard, rightly so, right? Who wants to live next to a high-level radioactive nuclear storage plant, right? So there's a lot of back and forth about this, but what we're looking for as geologists is a place where the water table is very low, so you don't want water to come in and corrode these drums. You're looking for a place that has no earthquakes, because you have a huge amount of underground waste, and you have an earthquake, you have a big problem. We're looking for places that aren't densely populated. So there's a lot of criteria that geologists spent 30 years looking through the United States. Where are we going to put this stuff? And the question maybe that should be in your mind is, what happens if, okay, we pick Yucca Mountain, we're going to start building on this, this is where all of our radioactive waste goes. What happens if you have a tanker with radioactive waste coming from, or a truck, coming from Pilgrim Nuclear Power Plant, driving through Boston, and there's an accident, and you happen to be on the Mass Pike with it? So there are many things to consider about this, but again, just talking about the mechanics of it, it's quite a simple procedure. That said, it's really neat being in the control room of a nuclear power plant because it's about the size of this room, and it is kind of like The Simpsons, kind of. Only the people are competent, and they have to go through these simulations. They have these simulation rooms where so there are people that are simulating a nuclear meltdown, and they test people every 6 weeks on what would you do. And there's it's really high stress level being in there. They're looking at everything. There's cameras, because the last thing on that slide was spreads knowledge of nuclear plans, right? You can modify this into a nuclear weapon. So there's all sorts of security and fail-safes in place. This we'll look at later when we look at hazardous waste, but just to briefly say, you have these drums, and the drums are filled with sand, and then they have these radioactive pellets and rods in them, and you bury them, you put them in a waste container with steel and lead, and then you bury them in a subsurface. This is intended to be a final sort of resting place. So with regards to who's using it and what the future is, the United States is phasing out. Japan was increasingly investing, but now they don't know what to do. It's an island, right? And there aren't a lot of coal deposits there. So this really, they're sort of on hiatus about planning the future of their energy sources. But after Fukushima, rightly so, they're kind of worried about this. United States, we have about 7%. We've decommissioned one. I keep calling Pilgrim Yankee because there was one Yankee power plant up in Rowe, Mass, top westernmost corner of the Mass, and that has been decommissioned. So we are steadily decommissioning these. The policy right now in the United States is more or less that the cons outweigh the pros. However, we need energy, right? And so, again, I told you McCain was talking about in a couple elections ago, we need to invest the heck out of nuclear power. So this is a big wild card. France, right, about 80%. Right, good, okay. So geothermal next. Geothermal is, refer to this. I'm so frustrated trying to talk about this in a very cursory manner because we could talk about each one of these for months. And look at the slides if you're interested. There are 6 different types of geothermal. I'll tell you about 2. One is where you make electricity. One is where you offset your electricity usage by bringing up water. Did we do this already? Why is it still on here? All right, then I've already told you. I beg your pardon. I'm now doing this in 4 different classes plus giving talks on it. I beg your pardon. So we did the pros and cons. I apologize. Fuel cells? We did? Okay. All right, so then we're pretty good. We can move on to minerals. This is the last part of a cursory discussion of energy. And it's the bottom line with regards to any course in energy on which you expand in a meaningful way. We can talk about these technologies all day, but the first thing we said in this class is, right, there's no such thing as environmental problems, there are only economic problems. There's the economics, right? So we can talk all day about needing solar, needing wind, needing geothermal. However, the bottom line is we use what's cheap. And not only is fossil fuel cheap, it's also quite versatile. Another piece of this, and again, and don't get political in this class, but I do let you know when it's relevant what policy has been suggested. 2 elections ago, when the candidates were talking about energy and the future of energy issues, there was one side, I won't even say which side, one side was talking about all these alternative energy technologies and we're going to invest in them and it's going to be great, which is good. That's good. The other side, though, said a lot about energy efficiency, which experts say is even better. You can sit and sing about windmills all day, but if you had every car on the road in the United States getting 42 miles a gallon or higher, you would completely eliminate our dependence on foreign oil, which has far-reaching economic and strategic and political consequences, right? If you have buildings with efficient HVAC systems, if you replace lights with LEDs, right, you are radically lowering the amount of energy that we use. In the next class, student presentations, this student put up this graph. Maybe I'll put that on Canvas as well, showing energy use through time of 10 major countries. And the United States is 3 times as much energy use per capita, each one of us, as any other countries. They all cluster down here for 20 years. And we're way up here and getting bigger. So if we can rein that in a little, that will have far-reaching environmental consequences with regards to sort of being more sustainable. So in this picture, again, this is in your slides, we have about half of our energy being wasted. So these are the types of energy inputs. These are the energy outputs. And then this is our US economy. Another kind of side note, when you graduate, if you get your own electric bill, sometimes electric companies will tell you, oh, you can sign on to pay a higher rate and you'll get green energy. That is such a marketing technique because you can't track energy. Energy companies make energy from many different sources and it just goes into the grid. So by you paying a higher price for energy, hoping that you'll feel good because you're using solar or wind, you can't track energy. That's a way for these energy companies, which are kind of wealthy, to get even wealthier, right? So no guilt needed if you click no thank you. But the energy that goes out, about 40%, 43% of it is unnecessary. Things like idling cars, leaving lights on, turning the heat up too high. The other 41% here is unavoidable energy waste. So I have a friend who's a doctor, and she was talking about how bad she felt that the ambulances idle and are sitting somewhere when they could be shut off and put away. I'm like, yeah, you know what, you save some energy by putting them away, but maybe somebody dies because the ambulance wasn't ready and got there in 3 minutes. So things like that are unavoidable, considered unavoidable energy waste. Maybe a tanker having to stop somewhere for permitting and then get somewhere else. So unavoidable energy waste. But you see, that's almost 85% of our energy in this country is wasted. So I always like to put a positive spin on things, and the positive spin here is that we have a lot of room for improvement. And this is a really simple thing that we can do. Cut down on energy waste on a personal level and also on a societal level, and it saves money. The things that will promote environmental sustainability save people money. You'll see this recurring theme when we talk about agriculture. So this is going to go off for a minute, and I'll swap over to the next slide. Does anyone have any questions or comments as I swap over? Okay. So we'll spend just a little bit of time looking at minerals and mining. Minerals and mining